Good morning, everybody. It's good to be back with you again. We are continuing the topic of talking about seismic slope deformations. Now, in the last lesson, we talked about how to evaluate whether or not you may have a slope deformation problem in a seismic event. But we didn't talk about in that lesson how to predict actual deformations that could occur. And that's what we're going to talk about today, is a simplistic method that engineers commonly use to estimate the deformation in a slope from an earthquake event. And so we call these methods Newmark deformation models. So quite often we're interested in, say we predict that a particular slope is going to move in an earthquake. The pseudostatic factor of safety was less than 1. And so we know the slope is going to move in the earthquake event, but now we want to know how much it's going to move. And so a popular approach that we use is this Newmark sliding block analysis. The Newmark sliding block analysis basically equates this sliding block or this sliding mass of a cross-section of a slope where the ground here is moving back and forth. It equates that to an equivalent block with a mass on an inclined plane, and that inclined plane is sliding back and forth. And so there's in both cases we have friction along the bottom of these masses that's preventing the block or the soil mass from sliding down slope. And so in this instance we're going to use the more simplistic problem of the block on the slope and estimate its displacements, and then we're going to equate that to the soil mass and its displacements. This method was first proposed and introduced by the famous engineer Nathan M. Newmark. He died in the early 1980s. He was a legend in the earthquake engineering community, considered by many to be one of the fathers of earthquake engineering. Much of his work was done in the 1950s, late 1940s, early 1960s, and it was really pioneering for its day. This method that he proposed is still in use today heavily, and it's because it's based on sound physics, and it's been validated to provide reasonable estimates of seismic deformations. Now bear in mind, it's far from perfect. To estimate the actual deformations in a slope, there's a lot of physics going on, and it's a very hard problem to solve. But this simplistic analytical method gets us within the ballpark, and so often that's good enough for us. So let's dive into the Newmark sliding block method. There's two cases we're going to look at. The first case is diagrammed here on the left. This is the static case. Now, as before, what we're going to do is we're going to evaluate the stability of our block in terms of a factor of safety. So I have a couple of forces going on. Of course, I have the weight of the block, but that weight could be rederived into a downslope component. And then, of course, from that weight and the friction on the bottom of this block, I have a resisting frictional force, and that is a oh, my daughter Julie just walked in. Hi, Julie. Are you going to take I'm recording a lecture, so hey, this is fun that my family gets to come in while I teach lectures. And oh, look, my daughter brought in her cockatiel pet bird too, so it's getting crazy in here, but I'm going to keep going. So anyway, it becomes a matter of calculating factors of safety. So in the static case, the factor of safety is the ratio of this resistance force divided by this downslope driving force that we can derive. Okay, and the way that we're going to do that is it's all just a game of angles. Now remember that the coefficient of friction here on the bottom of this block, that coefficient of friction mu, is equal to the tangent of the friction angle of the soil. Because remember, we're really tying this back to soil. And so what we need is the friction along the base of the soil, which is the friction angle. So this tangent of phi, that really is the frictional coefficient mu. Okay. So we can calculate then using this ratio. If we then cancel out the weights and then we do a little bit of trigonometry and simplification, it boils down to a very simple ratio. It's just the tangent of phi divided by the tangent of beta. And remember, beta is the angle of the slope. Okay. So that's for our static case. Now, the dynamic case would be the same, except now that we have an additional horizontal acceleration component going on and that we have to account for. And so that horizontal acceleration component, it's a function of time. So it's not a constant. It changes with time, because that's what an earthquake does. It changes with time. So if we account then for the addition of that acceleration in the driving force in the downslope direction, it's going to ultimately reduce our factors of safety for the dynamic case. So dynamic case is always going to have a lower factor of safety than the static case. So how do we actually get displacements though? Because that's just computing factors of safety, and factor of safety just tells us when we think the block is going to move, but it tells us nothing about how much movement. So when the factor of safety of our block in the dynamic case is equal to a value of 1.0, that is the acceleration then that corresponds to the acceleration that will just get that block moving. So we have a special term for that. We say then that the KH at that moment of time is equal to KY. And KY, as we introduced in the last lesson, is what we would call the yield coefficient. So the acceleration coefficient that gives you a factor of safety of 1 is the yield coefficient. So now we're playing a game of comparing KH to KY. And anytime KH is larger than KY, that means that the acceleration is larger than the acceleration needed to get the block moving. So that means then that we're generating relative velocity in our block. And if we're generating relative velocity, we're generating displacements. So it's going to look something like this. Here's a plot shown here on the top. And then we have some acceleration record that's going like this. And then we have some assumed constant yield acceleration. Okay? What we're concerned about is any time our acceleration exceeds that yield acceleration. Anytime it exceeds it, that means that we're starting to move. So once we exceed that yield acceleration, we start to generate velocity. And we can compute this velocity by integrating the area beneath that exceedance. So this is a triangular shaped area that's exceeding the yield acceleration, so that's going to produce then a parabolic velocity. Now, just because we drop below then the yield acceleration over here doesn't mean that all of a sudden we just go to 0 on our velocity. We have to slow down, so there's a ramp down period in the velocity. And so anytime we increase that relative velocity, we will always have a ramp down period. So then once we have our relative velocities plotted, we can then integrate the area beneath those, and then we can come up then with an estimate of displacement. So all the Newmark method is, the Newmark sliding block method is a method to using integration to get all the way down to relative displacements of our blocks sliding on the slope. Now, when researchers started applying this initially, they were predicting very large deformations that weren't matching reality. And people started asking questions going, what in the world is going on? And they started realizing that the experts were using for their yield acceleration the residual strengths of the soil, very, very low strengths, or strengths that correspond to high shear strain or softened soil. And soil doesn't always work like that, right? Oftentimes, if I were to plot, say, shear strain versus shear strength, oftentimes what we'd see is that soil will peak and then soften, and then we'll have some residual shear strength. So engineers were applying this residual strength at large strains to the entire time history record, but they were neglecting the peak strength of the soil at low strains. So these researchers wanted to account for that progressive failure and the softening effect of soil. And if that's the case, then the soil at low strains and early in the time history are going to have they're going to be stiffer, and so it's going to require a larger acceleration to get them moving. And then as the soil softens, the acceleration also softens. The yield acceleration also softens, to the point that after we've strained the soil enough, we'll eventually arrive at the residual shear strength, or the yield acceleration corresponding to the residual strength of the soil. But again, at the early part of the time history, we want to account for the peak strengths, or the yield accelerations that correspond to the peak strengths. So this method of accounting for the strain softening of the soil is what we call a modified Newmark approach. And these plots here, they show both, right? So here's the same time history we had before. This line right here is our constant yield acceleration at our residual strength. And then we have our modified yield acceleration that degrades with strain. So you can see early in the time history, the time history record does not exceed our initial yield coefficient, or our initial yield acceleration. It's not until right there that it begins to exceed it. And so once it begins to exceed it right there, and it experiences a little bit of strain right there, the soil begins to soften. And as it begins to soften, that yield coefficient reduces. So now it's a little bit smaller acceleration required to yield. And then we have some more exceedance right there. So we get much more exceedance in the modified approach. And as we exceed it, we soften the soil, and so eventually that yield coefficient comes down by the end of the record. But if we compare then these relative velocities, this is from the what I'm shading here in red is from the classical Newmark approach. And then if I change my pen color to something else, maybe blue, what we see down here is maybe from the modified Newmark. There's less relative velocity. And less relative velocity means less predicted displacement. So the whole point of the modified Newmark method is to account for the strain softening of the soil, and ultimately it's going to reduce the predicted deformations that you have. So you'll get smaller computed deformations with the modified Newmark method. Okay, so let's look at the math required to integrate these velocities and displacements. And let's just start with a very basic component. We're going to look at just a pulse acceleration. Okay, so this pulse acceleration goes from time 1 to time 2 as a constant value equal to large A. And let's say in this time period, the yield acceleration, A sub y, is equal to that value. So we are indeed exceeding our yield acceleration. So we're going to have relative velocity and relative displacement. So the difference between the acceleration that's applied by the ramp and the yield acceleration, this is the acceleration that's going to drive the displacement of our block. So it's really just this portion of the acceleration that we're concerned about. Okay, so here we go. First thing we're going to do is we're going to plot a couple of plots. On the top here, I've got acceleration versus time. So I've got my acceleration plot. Now down here, I'm going to have a relative velocity plot. And the way this is going to work is that I have on time, my daughter's pet bird says hi. Her name is Sunny. Okay, so at time 1, my plot starts right here. And if I integrate this flat line, that's going to be a slope line in velocity space. Okay, so that slope is just going to equal that constant value A. Now I've got another slope here down here that represents the yield acceleration, so it's going to have a lower slope, A sub y, and it's the area in between that I care about. So at time equals 2, A stops. So my slope at A just stops. And then it stays constant. It doesn't move. And it will stay constant until my yield acceleration slope catches up to it. So now I have this triangular area right here that I have to account for. And where those lines intersect, I'm going to call time 3. So the difference between the velocity from the applied acceleration and the velocity from the yield acceleration is the velocity that's going to drive my ramp. Sunny, you're being loud. So what I can do then is I can just take that triangular portion that's driving the ramp, and I can plot that now as relative velocity. Okay, so that's just that triangular portion. So with that, now we're prepared to integrate this relative velocity to compute displacement. So we're going to take that plot and we're going to do the same thing, but see, now this is a slope line. So if I want to integrate a sloped line, it's going to be a second order polynomial. And then this is a sloped line also, so that integrated is going to be a second order polynomial that has a decreasing slope to it. So this is how I integrate then, and I come up with a computed displacement d by the end of time 3. And that's a permanent displacement, meaning that's the displacement that the block slid down the ramp and is now stopped and waiting for additional yield accelerations and relative velocities. So I'm going to go back a couple of slides. This is the fundamental math for performing these calculations. Now, what if I have a time history that is a lot more complicated? In other words, I have a time history that looks like this. However, that acceleration with time, and this is time. So how does this apply? Well, what I can do is I can break this up into average blocks, right? And I can average those. So in other words, I can take these I can break this record up into a whole bunch of pulse accelerations, and the smaller my time step is, the more accurate I can make it. So obviously, if I use a computer to do this, and I can break this this acceleration record up into say 1,000 or 2,000, 10,000 time steps, I can come up with a very accurate representation numerically of what I would get if I solve this through closed form integration. So the point being, if I then did that closed form integration, what I would get is this equation right here for that little increment or that little pulse. The displacement is equal to this equation shown right here. So I can just extend this equation to all of my little pulses across a larger time history if I so chose. Okay. So here you are, you're learning about this method, and you say, wow, that sounds neat. I think I'd like to apply that in my projects or on my homework too. So there's a couple ways you can do it. One of the ways is you can solve your problem the exact same way we just talked about. You can develop an estimate of your yield coefficient. You could do a classical Newmark and have a constant yield coefficient the entire time, or you could do a modified Newmark and have a yield coefficient that degrades as the soil softens. Doing it by hand, it's possible, but it's going to take a lot of time and computation. Instead, I recommend some other tools. For instance, there's a software tool out there called Slammer, developed by a good friend of mine, Professor Ellen Rathje at the University of Texas, and it was U.S. Geological Survey research that was funded, and so the software was given to the USGS, and the USGS makes it available for free download to anybody who'd like to use it. It's very easy to use software. All you need to do is import a time history or a suite of time histories that you'd like to use, and then you can have default estimates of your yield coefficients, or you can enter slope or soil specific values from your own analysis, and then press run, and it will do all of the math for you and develop plots of velocity, acceleration, displacement, etc. So it's a very nice program, and it's available to you for free. You can search for it on the internet. The other approach, though, that you can use if you so choose is a simplified Newmark regression model. Now, what does this mean? Well, let me explain. It basically means that some of our researcher friends, they took a program like Slammer, and they took a whole suite of ground motions. Boy, I can do better than that. Here we go. Perfect. Okay, so then what they did was they took different ground motion parameters, so say maybe PGA, and they started plotting and running a whole bunch of these Newmark sliding block analyses, and they varied the yield coefficients, and they also varied the PGA. And so what they ended up seeing was Actually, I've got this plotted wrong. What they ended up seeing, here's displacement, okay, maybe in centimeters. And then what they did was they started plotting for different PGA values. Let's erase these. For low yield coefficients, I would get high displacement. So they would start to get data that would look like this in their different analyses. Okay, and this might be for PGA 1, and then they came along and they did it again, but for a different PGA. So maybe they got something that looked like this, so this would be PGA 2, and then maybe a different PGA, pick me a different color. So they came up with all these family of plots and data. So that might be PGA 3, where we have PGA 1 is less than PGA 2 is less than PGA 3. And they came and they would fit best fit functions to these different equations, and then they would try to develop then a statistical or numerical model to fit the data. The point being, if with these simplified models, if you have an estimate of your ground motion and you have an estimate of your yield coefficient, you can go straight to the line and come over and get your estimate of whatever your displacement is. Now remember, it's not perfect. There's scatter here, like we've talked about in the past, okay? And so with that scatter, you're always going to have a little bit of uncertainty, but you don't have to run a numerical analysis to do this. You don't have to integrate anything. It's just a straight empirical model. So you can plug it into a spreadsheet or whatever. So what we're going to do is just review now a couple of simplified Newmark models. They started in the 1970s, and you can see a lot of those models listed here. McDeese's seed was probably the most popular one for a very, very long time. The two, though, that I've used a lot in practice and that I want to talk about in this lesson are listed here. They were developed and published by Professor Jonathan Bray and his PhD student Travasarou in 2007, and then Professor Ellen Rathje and her student Saygili in 2009. Now these models, by the way, that we're going to talk about, they have both what are called scalar models and vector models. Now, the scalar model has one ground motion parameter in it, and the vector models have more than one ground motion parameter in it. And so the more ground motion parameters you include in the model, the less scatter and uncertainty in your prediction. So vector models are great, especially for probabilistic analyses where you're interested in minimizing your uncertainty, but they're a little more difficult to perform because they have more input parameters, more ground motions you have to put into. So what we're going to talk about in this lesson are just their scalar versions of the models, okay? So there's only one ground motion parameter we're dealing with. For the Bray and Travasarou model, here is the equation that we're given. Now, Bray and Travasarou, they do have a model that is just for peak ground acceleration, but I really like this version of their model where what they ask for is the spectral acceleration of the slope at a period of 1.5 times the natural period of the slope. So T sub S, that's the natural period of your failing slope. And he provided, or they provided, recommendations of how to estimate that. If you're doing a one-dimensional analysis, you can estimate it using this equation 4h divided by v sub s. So this would be, h is the, here, let's go to a plot and diagram it for you. Okay, so here's a cross section of my slope. Here's my failure mass. Okay, this distance from the top of the slope down to, say, the bottom of my failure mass, that height is h. Okay, and then the average shear wave velocity, not v sub v, v sub s, the average shear wave velocity in that soil mass is the v sub s that we use. So for one dimensional, we're going to use this equation right here. But if we want to consider a two-dimensional slope, then we're going to have this relationship here to estimate the natural period of the soil mass. Once we have that natural period of that failing mass, we need to go to a response spectrum for the site. So that's going to look something like this. So let's say that for that slope that we just drew, we would obtain through our seismic hazard analysis a response spectrum that looks something like this. Okay, now let's say, so then at a period of 0 seconds, we know that that's the PGA. But let's say through our calculation of the site period, we find out that the site period is right here. So if I were to go up, this value right here would equal the spectral acceleration at t equals t sub s. But what we want is a value of 1.5 times t sub s. So I'm going to go to that period on the response spectrum, and I'm going to come over. Coincidentally, that happens to correspond to about the same value of the PGA on my little sketch. That won't be the case in real life. So this would be spectral acceleration of period equals 1.5 times t sub s. So this is the value that we want for this model, okay, is that spectral acceleration for a period of 1.5 times the natural period of the slope. Moment magnitude we want to throw in there. Yield coefficient, everything else looks right. So, yep, this is our equation right there. And then if we want to account for the scatter in the model, Bray and Travasarou gave us their standard deviation. So we could estimate then like the 84th percentile, the 96th percentile displacement in the same way that we've done with other uncertain parameters in this class. Okay, that's Bray and Travasarou's model. For Saygili and Rathje, here's their scalar model right here. And this is just a function of the yield coefficient and the PGA. So remember, PGA is the spectral acceleration at 0 seconds or very, very close to 0, maybe 0.01 second we get from the response spectrum. So here's their relationship, and everything you see is based on this ratio of yield coefficient to PGA. but they also needed to correct their model for moment magnitude. So you can see that that's corrected right there. And then they give an equation for their standard deviation. This equation accounts for a phenomena that they observed with their uncertainty in computing what are called residuals. That's the error in the actual displacement versus what you predicted. And what they observed was that error was not constant with the ratio of ky over pga. So here's your word for the day. They observed that their uncertainty was what we call heteroskedastic. And so to account for that heteroskedasticity, yeah, that's a fun word. Try saying it. Heteroskedasticity. To account for that, they have an equation whose standard deviation changes as a function of your input parameters. So this is a heteroskedastic model. The previous model, where you have a constant uncertainty, is what we call a homeoskedastic model, or it incorporates homeoskedasticity, meaning it's uniform and constant. Okay, so as I mentioned before, this Saygili and Rathje has vector models that are more precise with less uncertainty, but you have to account for other ground motion parameters like peak ground velocity or area intensity in addition to the PGA. So we're just going to focus on the scalar model for this class. Okay, so now you have two models that you can use to simply estimate seismic slope displacements. To use those models, all you need is a yield coefficient and estimates of your ground motion parameters and design earthquake magnitude. There's a few things, though, you need to be aware of when you use these simplified Newmark models. A couple of them, you got to remember that these models, somebody had to run the Newmark calculations at some point. That's where the data comes from that these models are based on. And so when they ran these models and developed that data, they had to apply or use some assumptions. You need to be aware what those assumptions are. So it's best if you read the paper and know the limitations of the model, because these models are not applicable to all scenarios. They're just not. In order to account for epistemic uncertainty in our prediction of seismic slope displacements, it's best if you use multiple models. I've seen problems happen when engineers develop their favorite model and they just stick with it, but they ignore the other ones because they don't like the deformations that are predicted from those other models. It's best to use multiple models in order to try to capture the epistemic uncertainty in your problem. Finally, this is an issue that you'll run into, especially if you're wanting to do a coupled seismic slope deformation analysis with liquefied soil. So there's a large number of engineers out there that believe they can calculate or predict lateral spread displacements using a Newmark seismic slope displacement model in conjunction with liquefied residual shear strengths to calculate their yield coefficients. I have an opinion on that. I know that it's not very popular with a lot of people, but there are a lot of problems with the assumptions made in this calculation. One of the problems I want to poke at right here is that if you're going to do that type of analysis and you're going to use a simplified Newmark model, you need to remember that none of these models, like Bray and Travasarou or Saygili and Rathje, none of them had any data points in there in their development that assumed liquefied soil conditions. And liquefied soil, remember, is freaky stuff. It can be strain hardening, strain softening. It is very dynamic and complex. And so to try to represent it with a simplistic model like this, we may be completely off from reality. And just as a fan of statistics and modeling in general, I'll tell you that this type of practice is the definition of what we would call extrapolation. Anytime you use any model in a way that does not support the underlying data used to develop that model is extrapolation. So be very careful if you do this type of practice, and take those computed results with a grain of salt. So that's the end of the lesson. Thank you so much for your attention today. I hope you're doing well, and I hope everybody is healthy and safe. Please let me know if you have any questions, and I hope that you have a wonderful rest of your day. Thank you.